Hello students, in this video we'll learn about rotational dynamics. I am going to explain how to think and analyze the various forces which acts on the body during the circular or rotational dynamics and how to solve the rotational dynamics problem. So I am going to explain theory in this video. Let me first explain what is a circular motion. So circular motion is, you are very familiar, the tire rotates, the wheel rotates, any rotating object you have seen is a circular motion. So an object or every part of object revolving around a point or an axis is a circular motion. The motion is about an axis either outside or passing through the object itself. If you take the example of merry-go-round, you might have gone to the SL World or any other amusement park. You must have ride the merry-go-round. So if you're sitting in a merry-go-round, and if you consider yourself as an object, then you go in a circular motion around the center of the merry-go-round. So in that case, the axis is outside the object. But we take example of top spin. If you rotate it, or any disc that you rotate, then the axis is in the body at the center. So there are such various examples of circular motion, and we'll see some of the examples and how to solve problem related to that in subsequent sections. There are two main characteristics of circular motion: accelerated motion and periodic motion. Even though in a circular motion an object moves with a constant velocity, but the direction changes at every point. So that is the reason even the circular motion or uniform circular motion is called as accelerated motion. And why periodic motion? Because of the repetition. The object which goes in a circular motion, let's say it starts from point A, after some time it comes back again at the same point A. So it repeats that motion itself. So that is the reason it is called periodic motion. Let's look at the kinematics of circular motion and understand various kinematics. Angular velocity, omega. The W, which is called as omega in this case. As shown in the figure, the object moves from point A to point B and it sweeps through angle theta. Let's say that happens in time t. Then the rate of change of angle theta with respect to time is defined as angular velocity. For example, the object moves from angle 0 to 90 degree or the pi radians in 1 second, then we can define angular velocity is equal to pi by 1, which is pi radians per second. And the direction of angular velocity is given by the right hand thumb rule. So in the direction, you see the object is moving in anti-clockwise direction. So if you put right hand on that plane, then your fingers will show the direction of the object, but the thumb will give you the direction of your angular velocity. And the rate of change of angular velocity with respect to time is angular acceleration. For example, the object moves from 0 to 45 degree in 1 second, and from 45 degree to 90 degree in 0.4 second, and from 90 degree to maybe 360 degree in another 0.4 second, then the angular velocity is changing. The rate of change of that angular velocity is called angular acceleration. What is the tangential velocity? It's just a cross product of angular velocity and the radius. It's a vector product. So for example, the object completes one rotation. So the angle covered is 2 pi, and if that happens in 1 second, then we can calculate angular velocity as 2 pi by 1, which is 2 pi radians per second. Now, since it's complete one rotation, it covered a distance of 2 pi r, which is circumference of the circle. So you can define the linear velocity v as equal to 2 pi r divided by 1, which is 1 second, because it's covered in 1 second. So the linear velocity will be 2 pi r. But just now we calculated the angular velocity is 2 pi. So v is equal to 2 pi into r, which is nothing but omega into r. So that's how the tangential velocity is equal to omega into r. As it's a periodic motion, the distance covered in one rotation is 2 pi in time t, which is a periodic time. Therefore, the angular velocity, which is equal to distance covered in time, so distance covered is 2 pi radians in periodic time t. So you can say angular velocity is equal to 2 pi by t. And the frequency n is 1 by t, which gives angular velocity is equal to 2 pi n. Let's understand uniform and non-uniform circular motion. So here, object is moving with a uniform velocity, and the direction is given by right hand thumb rule. Now we add the acceleration to it, which is shown in red, and you see the angular velocity increases. So this particular example is a non-uniform circular motion. So uniform circular motion, speed is constant, only direction changes. The acceleration which is responsible for direction change is called centripetal acceleration, which is directed towards the center. So consider that object is moving in a circle. As per Newton's law, the object goes in a straight line unless and until some force acts upon it, right? But here it is not going in the straight line, it is going in a circle. So there must be a force which at every point it is pulling inside so that it can move in a circular motion. So that force is called centripetal force, and the acceleration is centripetal acceleration, which is given by omega square into r. For uniform circular motion, magnitude is constant, so centripetal acceleration is omega square into r. Since v is equal to omega into r, if we substitute value of omega, we get acceleration is equal to v square by r, which is equal to v into omega. In case of non-uniform circular motion, the velocity changes, which is caused by the acceleration directed tangentially along or in opposite direction. So if we take an example of a car wheel, it moves from rest to it takes some speed, okay? In that, the rate of change of angular distance, which is a angular velocity, that itself changes when we accelerate the car. okay, and when we apply the brake, the exactly reverse phenomenon happens. So this is a typical example of non-uniform circular motion of the wheel. Second example is fan. When you switch on the fan, its velocity will increase, tangential velocity. And when you switch off, the tangential velocity will decrease. So the force which is responsible, it acts tangentially along or in opposite direction. The change in velocity, we cause change in omega or angular velocity. Therefore, angular acceleration is equal to rate of change of omega with respect to time, which is dw by dt. Let's understand the dynamics of circular motion. You see in the animation how a mass, you can call it the point mass, having mass m tied to a string which is massless string. We always say it's a massless string because if you consider the mass of the string itself, the dynamics changes completely and become complicated. So to simplify the dynamics, we always say in circular motion the point mass attached to a massless string, inextensible, etc., etc. So to simplify the analysis of the motion, so look at this animation. It is moving with a constant speed. This is again accelerated, and once you cut the string, it goes in the direction tangential to the circular motion. Let's understand what is the centripetal force. Centripetal acceleration is towards the center, which causes circular motion because every time it is like pulling inward and try to keeping the circular track. So that's the centripetal force. The force is providing this acceleration is centripetal force, which is equal to m omega square r. Omega square r is a acceleration that we saw in the last slide, and force acceleration multiplied by mass is we get a force which is centripetal force. What is centrifugal force? Object with its own frame of reference is stationary. So if you see yourself, you are sitting in the merry-go-round. When it starts, the merry-go-round starts, you expect you're going out, you're going in outward direction. So you experience some kind of a force. But once you reach to the limit, or once you are sitting attached to the wall of this merry-go-round, you are stationary. So with your frame of reference, you are stationary. So, but there is some force which is pulling you inward, which is centripetal force, which is responsible for the circular motion. But you are stationary. There is a force, but you are stationary. So there must be a force which is acting exactly in opposite direction. So this force is called centrifugal force. So it's not a real force, but you experience it. So CFF, which is centrifugal force, is a net pseudo force, and CPF is a resultant of all real forces which act on the body and which causes the circular motion. So this is very important concept of what is the centripetal force. It's a resultant of all real forces. This sentence or this particular words are very important. You must understand this. Is a resultant of all real forces. That's the centripetal force, and which causes the circular motion. Now let's look at applications of uniform circular motion. Vehicle moving along a circular track. So this is a vehicle which is moving along a circular track having radius r and center C. If you look at from the plane in which the vehicle is moving, you can see center C and vehicle at the edge at the radius r. And if you attach a frame of reference to the center of mass of this vehicle, and then we'll try to analyze what forces are acting on that particular vehicle or object. So one obvious force is the weight itself, which is the gravitational force, you can say. And another force is the normal reaction from road on the vehicle. Because vehicle is not moving in vertical direction, so N is exactly balanced by the mg, because there is no vertical motion. Now, when you do the circular motion, the wheels of the vehicle are pushing the road, causing some frictional force. Okay, so road is pushing the wheels are pushing the road, and in return, road giving normal reaction, which is a frictional force on the wheel, which is towards the center. So that now frictional force you can very well define as coefficient of friction, which is mu s into normal reaction. So these are the three forces acting on the vehicle. So if you substitute value of N as mg, you get friction force is equal to mu s. As I said, what is a centripetal force? Which is sum of or resultant of all the real forces. So in this case, if you look at the force which is acting towards the center, is the frictional force. So that frictional force is responsible for the centripetal acceleration. So which is a centripetal force. So we can very well define Fs as is equal to mr omega square or mv square by r. And if you combine these two equations, mu s mg is equal to mv square by r, you get mu rg is equal to v square or v is equal to mu s rg. So that's how this is a velocity you can calculate based on the radius and coefficient of friction. So the velocity which attains by a vehicle in a circular motion will be governed by two factors. The first is the coefficient of friction and second is the radius. The more and more radius you increase, the more and more speed you can gain, and more coefficient of friction or rough road you can say, the more speed you can gain. So Vmax we can define as square root of mu s rg. Let's look at second example, well or wall of death, where a biker performs stunt in a well of death as shown in this animation. It is moving along the wall and having a radius of r. So let's analyze the forces which is acting on this biker who is moving in the vale of death. Again, we can attach the frame of reference to that biker, and the obvious forces acting on it is, of course, the weight and the friction force and the normal reaction from the wall. So these are the three forces which are acting on the bike or the point mass. So weight itself, then the frictional force balancing the weight because it's not performing any vertical motion, it is moving in the circular motion in the well itself. And the third is normal reaction N from well. So N is a normal reaction, and which we can very well say that is centripetal force which causes this circular motion. So we can say N is equal to mr omega square. And as there is no vertical motion, we can say the friction force is very well balanced by the weight itself. So friction force is always less than or equal to the mu into n, which is n is a normal reaction, because that's a maximum you can get as a frictional force. So Fs is not more than mu s, it has to be a little bit less than that. So you can put that for Fs, if you put mg, and for n you can put mv square by r, you get g is less than or equal to mu v square by r. In other words, the minimum velocity at which the biker can perform a stunt is square root of rg by mu s. So more and more friction you have, the Vmax can increase, but there is a limit to the friction. So V minimum is directly proportional to the radius and inversely proportional to the coefficient of friction. So that's how we did analysis of forces acting on bike when a biker performs a stunt in a vale of death. Let's move to next example. Vehicle on a banked road. Consider vehicle is a point mass and ignoring friction. So let's start with a simple case of ignoring the friction, and it's a point mass, because if we don't consider point mass, then we have to consider the momentum and other things. So for the simplicity, we are considering vehicle as a point mass. And let's analyze the forces. So this is a road banked with a theta angle, and the vehicle is moving, is performing circular. So it's like when you say the road is taken turn, okay, it must be having some banking. So that particular taking a turn, that motion is like a vehicle on a banked road which is performing a circular motion. Again, whenever we say it's a point mass, we can attach a frame of reference to that point mass and we can analyze the forces. So two forces are acting on vehicle. The weight acting downward, which is mg, and normal reaction n from road on vehicle, which is n, again at an angle theta to the y-axis. So if you resolve normal reaction, we get n sin theta and n cos theta. So after resolving, we can very well say that n sin theta, which is causing a circular motion, must be a centripetal force. So we can very well write n sin theta is equal to mr omega square or mv square by r. And as vehicle is not performing any vertical motion, we can very well say that n cos theta is equal to mg, which is the weight. So if you divide equation 1 by equation 2, you get tan theta is equal to V square by Rg, or the banking angle theta is equal to tan inverse V square by Rg. So we can very well determine the most safe speed Vs is equal to square root of Rg tan theta. So maximum speed is depend on the radius and the banking of angle. So the Vs can become infinite if angle is more than 45 degree. Okay, so vehicle will not skid at all. But below that there is depending on the value of tan theta, you can calculate the Vs and you can see what is the maximum speed it can gain with respect to the theta angle. So this is a good exercise, you can do it looking at the values of theta from 0 to 90 degree, and you can yourself see how the Vs varies. This is the speed limit for a given banking angle and radius. Now the question will come to your mind, why the bike slips? Okay, look at this video. This is a MotoGP race video. See, it skid. Now we can look at the second video. Oh, he also skid. So in the second video, if you look at very carefully, the reverse or the rear wheel, it lost the contact with the ground. Okay. So the contact point is very small when they take the turn, and therefore not providing enough friction force, and that is the reason bike slips. So let's look at the role of frictional force. So in case of maximum, what is the maximum velocity? So as you try to get on the circuit track, if you try to go with a more velocity, let's see what happens. So at velocity increase, the bike tried to skid, but because of it's a friction force which pulls back and try to put bike on the same track. In case of minimum velocity, it tries to go down, okay, but it is friction force which tries to pull up and put on the same track. Okay, so this is how the frictional force works in case of maximum velocity and minimum velocity. I hope this is clarified how the frictional force works on the bike or any vehicle in a circular motion on a banked road. Let's analyze forces for minimum velocity. So as velocity decreases, bike tries to go down, but it's the friction force which keeps it on the same track where it is moving. So force acting on vehicle are the friction force itself, which you can say Fs, gravitational force mg, and normal reaction N from road on vehicle. So these are the three forces, real forces, which are experienced by the object during the motion. There are no other forces. So if you resolve the forces as shown, so let's resolve normal reaction and let's resolve the friction force. So you get n sin theta, n cos theta. N sin theta is along the minus x-axis, n cos theta along positive y-axis, and friction force Fs cos theta along x-axis and Fs sin theta along y-axis. So you can very well say that the weight or the gravitational force mg is nothing but summation of Fs sin theta plus n cos theta, because there is no vertical moment. Okay. But the centripetal force, which is mv square by r, is the resultant of all real forces. So if you look at the, say, along the x-axis, the forces are n sine theta and fs cos theta, and mv square r is toward the center, which is minus mv square by r, is equal to minus n sine theta plus fs cos theta, and if you multiply by minus, you get mv square by r is equal to n sine theta minus fs cos theta. And friction force is nothing but coefficient of friction and the normal reaction. If you substitute the fs value and take n cos theta out from equation 1 and 2 and divide equation 2 by 1, we get minimum velocity is equal to square root of rg into tan theta minus mu s divided by 1 plus mu s tan theta. So that's the minimum velocity for a circle motion on a banked road. Now let's analyze forces for Vmax. In case of maximum velocity increases, it tries to skid, but it's a friction force which brings back and keeps on the track. The forces acting on vehicle are frictional force Fs, the gravitational force mg, the normal reaction from road n. So these are the three real forces acting on vehicle. If you resolve the forces, friction force as Fs cos theta and Fs sin theta. Fs cos theta is along minus x-axis, Fs sin theta along minus y-axis, normal reaction n cos theta along y-axis and n sin theta along minus x-axis. We can very well say that mg or minus mg minus fs sin theta is equal to n cos theta, and if you multiply with minus, you get mg is equal to n cos theta minus fs sin theta. And the centripetal force, which is responsible for the circummotion, which is mv square by r, we can very well say it's a sum of n sin theta plus fs cos theta. And friction force is nothing but coefficient of friction into normal reaction. So if we substitute value of fs and take n cos theta out from equation 1 and 2 and divide equation 2 by 1, we get maximum velocity along the bank road theta with a circular track of radius r. The maximum velocity is square root of rg into tan theta plus mu s divided by 1 minus mu s tan theta. So that's how we see how the friction force plays a role and what could be the maximum velocity and what could be the minimum velocity. Now let's look at the conical pendulum. So what is a conical pendulum? A conical pendulum is a point mass m called bob attached to a massless string rotating in horizontal plane as shown below. So this is a massless massless string, inextensible. So with a weight or force, there will be no expansion in the string, and it's a massless. A bob or point mass is attached having mass m, and it is rotating in a horizontal plane as shown. Now let's analyze the forces on the bob. There are only two forces, and let's attach a frame of reference to the point mass. You can see it's a gravitational force mg which is acting on the bob, and the tension TO in the string due to which it's not going down. Okay, so that string is holding, and Bob performing a motion, circular motion, and that creates a kind of a cone. Okay, that's why it is called conical pendulum, and it's a circular motion, so it's a periodic motion. So that's the tension in the string. So if you resolve the tension as shown, okay, TO sin theta and TO cos theta, you can very well say, as Bob is not moving in vertical direction, that means gravitational force is balanced by the tension component. So mg is equal to TO cos theta, and horizontal component of tension is providing centripetal force for the circular motion. So you can very well say mr omega square is equal to TO sin theta, and the radius r is equal to L sin theta, where L is the length of the string. So from this equation you get omega square is equal to square root of g by L cos theta, and we know that omega is equal to 2 pi by t, so you get periodic time t is equal to 2 pi by under root, or 2 pi into square root of L cos theta by g, which, and frequency is equal to 1 upon t, so therefore you get frequency is equal to 1 upon 2 pi under root of g by L cos theta of a conical pendulum. Now let's look at the vertical circular motion. Before explaining various applications or various scenarios of vertical circular motion, I know you have learned the conservation of energy, but let me explain again, which is relevant to this vertical circular motion understanding. So object of mass on ground with velocity Vg is moving upward. Its energy at ground level, because it's a pure kinetic energy, so you can very well define energy at ground level is equal to half m Vg square. So Vg is the velocity at the ground. As moved to height h by 2, the velocity becomes Vh by 2, which will be less than the velocity at the ground, because some of the energy will transfer in the potential energy. So its energy at h by 2 is equal to half m Vh square plus mg h by 2, because it traveled by a distance h by 2, which is converted into potential energy, which is mg h by 2. As it moves to height h, the velocity becomes 0, and its energy at h is equal to mgh. And when it falls from height h and reaches to the ground, it will gain velocity vg. In the entire scenario, we did not consider any frictional forces or any wind forces or any other forces. So this particular example, we said that it is happening in a vacuum. So that's how it gets the, so this is a kind of a conservation of energy. I explained this because this is going to, this phenomena of conservation of energy we are going to use in analyzing the vertical circular motion. Now, point mass undergoing vertical circular motion under gravity. The first case, mass tied to a string. At any point, there are only two forces acting on the bob. The gravitational force mg and variable tension in the string Tv, because when it is at the bottom the tension will be different, at the top tension will be different, when at the 90-degree tension will be different. So let's consider the bob at the uppermost position A. The forces acting on the bob is mg and tension Ta at point A. So centripetal force is resultant force of all forces. Therefore, we can say mva square by r is nothing but a resultant of all real forces, which is mg plus Ta. So for minimum possible velocity, Ta should be 0. Because if Ta increases, the velocity will increase. So for minimum possible velocity, Ta should be 0. So we get Va minimum is equal to square root of Rg. So minimum velocity is the square root of Rg. So at R increases, the Va minimum will increase. Now consider bob at the lowermost position B. Again, there are two forces acting on the bob at position B, which is the weight or gravitational force and the tension Tb. So the resultant of these two forces is the centripetal force responsible for the circummotion. Therefore, we can say Tb minus mg is equal to mvv square by r. As it moves from position A to B, loses potential energy equal to mg into 2r. So essentially it lost, it traveled to height h, which is h is equal to 2r. So it lost that potential energy. Therefore, in the kinetic energy, the potential energy got added. So therefore, Vb has to be greater than Va. So you can very well say that sum of kinetic energy plus potential energy at point A, which is 2 mgr plus half mva square, is equal to the kinetic energy at point B, which is half mvb square. So if you rearrange, you can very well say 2 mgr is equal to half mvb square minus half mva square, which gives you, if you rearrange, vb square minus va square is equal to 4rg. So the minimum speed at B is equal to square root of 5rg using Va minimum is equal to Rg. So from equation 2, substituting equation 1 from 2 and 3, we get Tb minus Ta is equal to 6 mg. So that's how we analyze how the forces will act on the bob at lowermost position B and how we can calculate the tension and the velocity. Let's consider the bob at horizontal position C and D. Again, same two forces will be acting on the bob, mg, which is the weight or gravitational force, and the tension Tc and Td. They both are equal at this point. So the resultant net or the resultant force of real force is a cause of circummotion. So we can very well say Tc is equal to Td is equal to half m v square. So velocity at C or D. So it moves from position A to C. It loses potential energy equal to mgr. So from A to C it loses, but from moving from B to D it gains. Okay, but the magnitude is same, mgr. So therefore you can say Vc is greater than Va. So you can very well write mgr is equal to half mvc square minus half mva square, which gives you Vc square minus Va square is equal to 2gr. So you can very well calculate Vc is equal to Vd is equal to under root or square root of 3gr using VA minimum is equal to square root of RG, and this gives you TC minus TA is equal to TD minus TA is equal to 3 mg. Now consider point mass undergoing vertical circular motion under gravity. The second case, mass tied to a rod. So at any point, so mass is tied to rod, so it is not like a string, it will not sag. Even it goes on the top position A, it will not sag. Okay, so when it will not sag, that means the velocity at point A could be 0. Okay, so at any point there are only two forces acting on the ball: gravitational force and variable tension in the string. So in case of rigid rod, practically zero speed is possible at point A, and that gives V lowermost minimum is equal to 2 root Rg using Vb square minus Va square is equal to 4 Rg, because Va you can put 0, so Vb you get 2 under root Rg. So that's at the lowermost position the minimum velocity we can get. So V minimum at C and D is equal to under root 2 Rg using Vc square minus Va square is equal to 2gr. Now next look at the sphere of death. So here biker are performing the stunts and they are going in a circular motion. So this is a sphere of death. The dynamics of sphere of death is same as vertical circular motion. Only difference is the tension is replaced by the normal reaction from the sphere. The linear speed is same. If it goes in a constant speed, okay, the linear speed is same. But the angular speed is more for small circle and angular speed will be less for large circle. So when they are performing stunt at the bottom, you see they are revolving very fast, but when they come at the center, they are taking little longer time to complete the rotation. So that's how angular speed is more for small circles and angular speed less for large circles. Now again, one more application, we can analyze vehicles at the top of convex overbridge. So consider vehicle at top of convex overbridge. So this is a convex overbridge and you can consider having radius r. There are two forces acting on the vehicle. If you consider that vehicle as a point mass and attach a frame of reference to that point, you can see the force, gravitational force mg acting downward and normal reaction acting upward. The resultant of there are two forces, which is centripetal force responsible for circular motion of a vehicle. So can very well say the resultant force is mg minus n, which is responsible for the circular motion, and that must be mv square by r. And just to maintain contact with the bridge, n has to be 0. So that gives maximum velocity is equal to square root of Rg. So you can say how much fast I can go over the bridge. The answer is square root of Rg.